Good weekend. Last week of classes. So, let's see. Looking forward, what we're going to do in the next couple of classes is we're going to finish up talking about spin angular momentum and its properties. And then we're going to look at the behavior of a spin in a magnetic field. And that will be everything that we do this week. So let's think about what we know so far. We're talking about electrons and being spin 1/2 particles. And so the Z component of the spin has eigenvalues of plus h bar by 2 or minus h bar by 2. What we said is we could write a general spin state as some fraction in alignment with a spin up state and some fraction in alignment with the spin down state. Where the spin down state has the eigenvalue minus h bar by 2 and the spin up state has an eigenvalue of plus h bar by 2. We spent some time kind of writing down matrix representations of all of these, of the SZ eigenstates, and they were simple. They were just two element column matrices, 1, 0, and 0, 1. So if I had a general state was A times chi plus B times chi minus, I could represent that as a column matrix, just AB, and that's it. Then we wrote down matrix representations of all these operators that we use. And the way we did it is we thought of it as like kind of pre-computing all of the inner products that you need to get an expectation value. And these were all the results that we got. The S squared was particularly simple because it's just the identity matrix multiplied by some prefactor. That prefactor is the eigenvalue of the S squared operator. It is h bar squared S times S plus 1. And if you put in S equals 1/2, you get 3/2 times 1/2, which is the 3/4 prefactor out front. And then we did the same thing for all of the other types of spin operators that we might have. So the SZ and S squared are the most important, but we also had the raising and lowering operators. And then we had the Sx and xy, which we could express in terms of the raising and lowering operators. And so now that we have all these things defined, what I want to do is I want to be able to work with them to solve some problems. And what we're going to do today is we're going to say, well, that's all great, but so far we have only the eigenstates of the Sz operator. What happens if we had, say, Sx? What's that going to look like? This is wrong. So what we want is we want to see an eigenvalue type equation where we take our Sx operator, act on some state. We want to get that state back again with an eigenvalue multiplying. So we're looking for something of this form, but we've already written down the matrix representation of a general spin state and of the Sx operator. And so we want to solve this eigenvalue equation. We've done something like this. We did one example where we did this type of eigenvalue equation, but let's do it again. Let me remind you, the way that I like to think of it is what we could do is we could multiply this column matrix by the identity matrix, and that's not going to do anything. So I'm going to insert the identity matrix, and we'll put our column matrix in there. And now what I can do is I've got square matrices on both sides, so I can subtract the right-hand side from the left-hand side. And if we did that, we would get h bar. So let's do it this way. I'm going to subtract off lambda times 1 for the 1, 1 element, and so I'll get a minus lambda. And then for this element, I'll just have 1 times the h bar by 2. So h bar by 2. And then let's see, h bar by 2 again. And then we subtract off the lambda for the remaining element right there. And that all multiplies AB. And because we moved everything from the right to the left, that has to be equal to 0. Okay, and the way we find our solutions for lambda is we take the determinant of the square matrix and set it equal to 0. So we have minus lambda h bar by 2, h bar by 2 minus lambda. The determinant is going to be the product of this diagonal minus that diagonal. So it's going to be lambda squared minus h bar by 2 squared is equal to 0, and therefore lambda is equal to plus minus h bar by 2. And so that's kind of interesting, I guess. It means that the Sx spin operator has the exact same eigenvalues as the Sz operator. So if you measure Sx for a spin 1/2, you will definitely get either plus h bar by 2 or minus h bar by 2. What's more interesting is actually writing down the eigenvalues and then finding some of these probabilities. What is the probability of measuring either plus or minus h bar by 2 for the x component of the spin? So to get the eigenstate, we're going to sub, let's start with the plus h bar by 2 into our characteristic equation. And so our characteristic equation is going to be something like minus a times lambda plus b times h bar over 2 is equal to 0. So I've just taken the first row of our square matrix and I multiplied by the column of our AB column matrix. And then on the right-hand side, that has to be equal to 0. And so we're just going to put in plus h bar by 2 right here. But you can probably see already what that's going to do. If I have h bar by 2 in both of my terms, I can divide by h bar by 2. And it's just going to be minus a plus b is equal to 0. Which is going to mean a and b have to be equal to each other. So therefore, minus h bar over 2. Let's do a plus h bar over 2b is equal to 0. Can cancel the common factors, and we get that a is equal to b. So at this point, we can arbitrarily pick a value. Usually people just pick 1. And so then your eigenvector is just a 1, 1. If you want it normalized, we put a factor of 1 over root 2 out front. And so therefore, the eigenvalue for Sx equals plus h bar by 2, let's say goes to plus h bar by 2 is chi plus, but what we'll do is we've already used chi plus for the z component of the spin eigenstate. And so let's put a little x here to remind us this is specifically for the x component. These are the eigenfunctions for the Sx operator. It's going to be 1 over root 2, 1, 1. And that's normalized. Yep.
Do you mean eigenvector or eigenvalue?
Sorry, yeah, you're right. Eigenvector or eigenstate. Yes, that's true. You are correct. Good. Okay. And then to get the other one, instead of putting in the plus h bar over 2 here, I would just put in the minus h bar over 2. And the minus sign and this minus sign will cancel. Again, we'll cancel the h bar by 2. And we'll have a plus b is equal to 0, or a and b are equal but opposite in sign. So subbing in lambda equals minus h bar over 2 into minus a lambda plus b h bar over 2 equals 0 gives a is equal to minus b, or maybe I'll write it as b is equal to minus a. And so the eigenvector for the minus h bar by 2 state is chi minus x is 1 over root 2, 1 minus 1. And what you could do is you could confirm that these are orthonormal. If I took the inner product between these two, I would transpose one of these and then just do the matrix multiplication. You can see we're going to get a 1 times 1 plus a 1 times minus 1, which is 0. So they are orthogonal. Okay. So therefore, a general spin state, which we initially wrote as A times chi plus times B times chi minus, was this little simple row matrix. This is in terms of the Sz eigenstates, but I could rewrite it in terms of the Xx eigenstates if I wanted to. So we can expand in terms of chi plus minus for the x. Well, let's see. I've got both chi plus x and chi minus x on the screen here. Let's just imagine that we added those two. Well, if I add the two, the minus 1 and the plus 1 in the lower position, the B position, will cancel. And we'll just be left with something like 2 over root 2, which is root 2 and 0. So if I divide by root 2, that gives me the original Sz state. So, for example, chi plus is equal to 1 over root 2 chi plus x plus chi minus x. And likewise, the z component spin down state is the difference between chi plus for the x minus chi minus for the x. And so it looks exactly the same, except the sign is different between the two. All right. So what we'll do is we will, for chi plus, substitute this, and for chi minus, we will substitute this. All right. So what are we going to get? I wonder if we can do this mentally. All right. So chi plus is going to have a chi plus x with a positive sign, and so is the chi minus. So we're going to get an a plus b. So we should get an a plus b. Both of them have a 1 over root 2 factor, and then chi plus x. And then we want to have a chi minus x here. There'll be a 1 over root 2. Let's see. If I put in the chi plus here, I'll get a plus chi minus x multiplying the a. And over here, I'll get a minus chi minus x multiplying the b. So it should be an a minus b. And I think that's probably right. Okay. So remember what these coefficients tell us. These coefficients, if we square them, they'll tell us the probability that our measurement will yield this state is given by the square of this coefficient. The probability that an Sx measurement will yield this state will be the square of this coefficient. So the square tells us the probability that a measurement of Sx will yield, in this case, the chi plus x state. And so this one gives us the probability of getting the chi minus x state if I square it. Okay, so let's just check something. Let's check that a plus b over root 2 times, it's the absolute square. So remember, we have to take the conjugate. So if I take the probability of getting the spin-up state along the x direction and add it to the probability of getting the spin down, they better come out to be 1. And so let's just verify that that actually works. Minus b conjugate over root 2, like so. Okay. So everything's going to have a big factor of 1/2 out front. So I'll just put a big 1/2 out front. And then what are we going to get? A times a star is going to be a squared. And then we're going to get a times b star plus, let's see, b times a star, and then plus b squared. Okay, and then over here, we're going to get a squared again. And then let's see, we're going to get a minus a b star. That's nice because we can immediately cancel those terms. And then we're going to get a minus b a star. Okay, and we can cancel those terms. And then we're going to get a minus b times minus b star, which is plus b squared. And let's see, a squared plus a squared is 2a squared divided by half is just a squared. And so this comes out to be a squared plus b squared, which we already said had to be equal to 1. And so that works out nicely. All right. So with all this in mind, we can just start trying some example problems. And so let's try the following. This is exactly lifted from the textbook. So a spin 1/2 particle is in the state. Okay, we'll just make something up. 1 plus I over 2. So there's a 1 over root 6, and then it's 1 plus I and 2. You can mentally see that this is going to be normalized, I think, because if we take the absolute square, I'm going to get a 4 here, a 2 here. Add them up, that's a 6. Divide by root 6 squared, that's 1. So it's normalized, so that's good. So the question is going to be, find the probability of getting plus h bar 2 and minus h bar 2 with a measurement of Sz. Okay, so the strategy is the following. I want to take this general state and expand it in terms of the Sz eigenstates. So we want to expand chi in terms of the Sz eigenstates, which are chi plus and, well, chi plus is 1, 0, and chi minus is 0, 1. Okay, but that's pretty easy to do because we can just write the following. We could say, well, I'm going to have an a times chi plus a b times chi minus. And I just need my a coefficient to be 1 plus I over root 6. And I need my b coefficient to be 2 over root 6. Okay, so chi could be expressed as 1 plus I over root 6, 1, 0, plus 2 over root 6, oops, 0, 1. All right, but that's just 1 plus I over root 6, I plus eigenstate, plus 2 over root 6, chi minus eigenstate. And so now we can just directly read off, this is my A coefficient, and this is my B coefficient. If I want the probability of getting spin up, it's A squared, the absolute square. And if I want the probability of getting spin down, it's the absolute square of B. So, therefore, the probability of getting plus h bar by 2 for sz is a squared, which is going to be 1 plus I over root 6, 1 minus I over root 6. And let's see, 1 plus 1, so it's 2 over 6, and that comes out to be 1/3. All right. So we better hope that we're going to get 2/3 for the probability of getting spin down. And you can already see if I square b, it's 4 over 6, which is 2/3. So the probability of getting minus h bar by 2 for sz is b squared, which is 2 over root 6 squared, which is 2/3. All right, good. So that's kind of the straightforward example. It's very easy to rewrite a general spin state in terms of Sz eigenstates. But I don't have to always do Sz. I could do the same thing for X. And so the next question is, well, okay, before we do X, let's do this. Let's ask, what is the expectation value for sz? Okay, so I want the expectation value of sz, which is going to be chi dagger times sz times chi. All right. So I'll leave it to you to show that, as you might expect, it's going to be this weighted sum. And the sum is going to be weighted by, it's a weighted sum of the eigenvalues. One eigenvalue is plus h bar by 2. The other one is minus h bar by 2. And the weighting factors are the squares of these coefficients, the probabilities. We already know that this is a third and this is 2/3. And so this is equal to h bar by 2, 1/3 minus 2/3, which is minus a third. And so this is minus h bar by 6. And so that's your expectation value. So these are stationary states, just like we talked about the stationary states of the infinite square well and the harmonic oscillator. Once you are in one of these stationary states, you stay in those stationary states, and the expectation value will stay like this until you do a measurement that collapses the wave function. Okay, so then the follow-up question that I wanted to do is, so let's find the probability that a measurement of Sx yields plus h bar by 2 and minus h bar by 2. The strategy is exactly the same. It's just that it's a little more, I don't know, it's not hard, but you have to pay more attention about how do I expand my general spin state into the S plus X and X minus X eigenstates. So we want to expand chi in terms of S plus X and S chi minus X. Okay. All right. So let's just remind ourselves, chi plus X was 1 over root 2, 1, 1. Chi minus X was 1 over root 2, 1 minus 1. All right. So we already know that the general state we were given was 1 over root 6, and then it was 1 plus I and 2. And we already know that we can write that in terms of the eigenstates of the Sz operator. So I'll just write that down again. So that's what we already previously worked out. This is 6, sorry, root 6. But we also know how to rewrite these in terms of chi plus and chi minus. So use the fact that, let's see, chi plus was 1 over root 2 times the sum of the X eigenstates. And chi minus was 1 over root 2 times the difference of the X eigenstates. So what we could do then is take this, oh, whoops, I went too far. Where is it? Right here. That's going to go in here. And then this one is going to go into here. Okay. So let's just write it out. So therefore, chi is going to be 1 plus I over root 6. And now we're going to have a 1 over root 2, and chi plus is chi plus X plus chi minus X. And then it's plus 2 over root 6. 1 over root 2. Chi plus X minus chi minus X. All right. And now all we want to do is we want to collect the chi plus X's together and the chi minus X's together. Okay. So let's see, there's going to be an overall root 6 times root 2. So that's root 12, which is the square root of 4 times 3, which is 2 times the root 3. So there's going to be a 1 over 2 root 3 out front. Okay. And then the chi plus X is 1 plus I, and then plus 2. So it's 1 plus I plus 2 chi plus X. And then what about the minus? It's 1 plus I minus 2. So 1 plus I minus 2 chi minus, at least I hope it is. Let's see If that agrees with what I have written down, yes. All right. So 1 over 2 root 3. 3 plus I plus x. And then it's going to be minus 1 plus I minus x. Okay, good. And so, the hard part's done. Because the questions to all of, or the answers to all of the questions are just going to be determined by these coefficients. If I want to know what is the probability of getting plus h bar by 2 along the z direction, it's 3 plus I divided by 2 root 3 absolute square. If I want the minus h bar by 2, it's minus 1 plus I divided by 2 root 3 absolute square. And we better hope that those come out to be normalized. So let's try. Okay, so therefore, the probability of a Sx measurement giving plus h bar by 2 is, I'll call it ax squared, the coefficient for our x expansion. And so that's going to be what? 3 plus I times 3 minus I divided by 2 root 3 squared, which is going to be 12. Okay, but 3 times 3 is going to be 9. And then I times minus I is going to be plus 1. So it's 10. 10 over 12, which is 5 over 6. So this is 5 over 6 is our probability. And then the probability of a Sx measurement giving minus h bar by 2 is bx squared. And our b coefficient is minus 1 plus I. So we're going to get a minus 1 plus I times minus 1 minus I divided by that same 12. And let's see. Minus 1 times minus 1 is plus 1. I times minus I is plus 1. So we get a 2. 2 over 12 is 1/6. So this is 1/6. And of course, we can see immediately that these probabilities add to 1. And so that's good. And so you can see here the real trick to solving these problems efficiently is by expanding your general state in terms of the most convenient eigenstates, the most convenient basis. For a measurement of Sz, it's the Sz eigenstates that you want to expand in terms of. For a measurement of Sx, you want to expand in terms of the x eigenstates. So likewise, the expectation value for Sx is, let's see, well, it's just going to be ax squared, h bar by 2, plus bx squared minus h bar by 2. But we've already worked out the square of these coefficients. It is 5 over 6. Let's do it this way. H bar by 2, 5 over 6 minus. Okay, let's see. H bar by 2. So we're going to get a minus sign from the eigenvalue, and then we had a 1/6. And so 5/6 minus 1/6 is 4/6, which is 2/3. And then we have a 1/2 out front, and so it should be just h bar over 3. I think. Yeah, that is what I've got written down here, so that's good. All right, perfect. So, um, that's kind of an example of how you can use these matrix representations of spin operators and eigenstates to calculate probabilities and expectation values. And, no matter what problem they throw at you for these systems of just two states, they're all going to play out just like this. All right. So we're only going to do one more topic in 304, and that is what happens if we put a spin in an external magnetic field. Okay, so spin we're going to show is acts like a little magnetic moment, and it's going to interact with magnetic fields. So let's see how it all works. So this is 4.4.2 electron in a magnetic field. And so as we go through this, what you can have in the back of your mind is NMR or MRI. So the physics of what we're about to talk about is directly applicable to MRI, which is used to get these high contrast images of stuff that's happening inside your bodies, like tumor growth and stuff like that. All right, so we'll start with just a classical picture, and then we will kind of write down the quantum analog or the quantum details. So I want to imagine a spinning ball of charge. So a spinning ball of charge has a magnetic dipole moment. And what we'll use for that dipole moment is the symbol mu. Um, and so it's relatively easy to understand why a spinning ball of charge would have to have a dipole moment. Current is a source of magnetic field. So anytime I have a moving charge, it creates a magnetic field. So if you imagine a uniformly charged ball, or if you want, just a ball that has a surface charge, if we spin it about its axis, then I could pick one little piece of that charge and it's going around in a loop. And you know that if you have a current moving in a loop by the right-hand rule, the magnetic field through the center of that loop is in the direction of my thumb, up. So if I look down, a counterclockwise rotating positive charge would make a magnetic field up through the center of that loop. Okay, so I could try to draw a ball of charge. And what I'm going to try to do is make some kind of axis, and I suppose that my ball is spinning about that axis. And then we decide, okay, over here is a little chunk of the ball, and that little chunk carries charge dq, and that dq is orbiting around this axis. So I guess in this direction, the way that I've drawn it. And so if this dq happens to be positive, then I can just do my right-hand rule and say it's going to make a magnetic field up through the center of that loop. And I can do that for all of the little dqs that make up the entire sphere. And if I add up all of their contributions, that gives me the total magnetic field. And then from there, you can go on and define your magnetic moment. So for example, this little ring or this little loop of charge, this little current loop is going to make some magnetic field dB here, which is going to contribute to the overall magnetic moment mu. All right. Okay. So quantum mechanically, the dipole moment, the magnetic dipole moment, mu, associated with a spin is mu is equal to some proportionality constant gamma times the spin. All right. And so I can't derive that from anything more fundamental. It's experimentally observed to be the case. And this gamma is called the gyromagnetic ratio. The reason it has this kind of gyro terminology in here is because let's just imagine that classically you did spin a sphere. Well, that spinning sphere is going to have a spin angular momentum. And now if you coat the sphere with charge, then it has spin angular momentum and a magnetic moment, and they are proportional to one another. If I increase the angular momentum by having the sphere spin faster, then the current goes up of the spinning charge and the magnetic moment goes up in the same proportion. And so there's this intimate relationship between spin, angular momentum, and magnetic moment for charged classical spinning objects. And then that carries over for our quantum particles. And so this gamma is somewhere around 2 for an electron, actually -2. All right. So what I want to do next is I want to turn on an external magnetic field. And so we turn on some external field that I'll call B. Okay, so in an external magnetic field, the dipole moment experiences a torque. If you like, just think about a compass needle. A compass needle is like a little bar magnet. It has a north and a south pole. It has a dipole moment. And if we put it in Earth's magnetic field, the North Pole tends to align with the north going magnetic field lines. And so the same thing is going to happen with our little magnetic moment in our spinning particle. It tends to tilt towards the external field. Experiences a torque which tends to align it with the external field. And this is like a compass needle. So we'll write down the details, but it's worth just trying to understand intuitively why that happens. Let's imagine that I force this magnetic moment to be perpendicular to that external field. So it's going to try to snap back. So when I force it down here, I'm giving it substantial potential energy. Potential energy is a really good name because if I was to release that, the dipole would start rotating. It would gain kinetic energy as it loses potential energy, at least classically. And so what we expect is there must be some force causing this rotation. And so we describe that as the torque. So let's see if we can work out some of those details. So the energy of a magnetic moment in an external field. I mean, no doubt you've already done this in a lot more detail in a course like 301. Okay, but let's do this again anyways. So we'll start with our dipole moment mu. We'll attribute that, if you like, to some kind of current I. And so, the dipole moment is roughly the field loop center times the area of this little current loop. And then what we do is we turn on an external field, B, and we'll just say that B is aligned with the z-axis. And then we're going to define an angle theta between B and mu. And I'll draw it in this direction because I'm treating B as like our z-axis, and then we usually measure theta relative to the z-axis. Okay, so the torque is going to be given by mu cross B. And so the magnitude of this torque is going to be mu B sine theta. All right, now B tends to cause the dipole moment to align with the external field. So B causes theta to decrease. So in a short time interval, then, our change in theta is negative, right? I'm measuring positive theta this way, but mu is going the other way. So the change in theta is negative. Okay. Now, if we were talking about linear motion, we would talk about things like force times displacement is work. And by the work kinetic energy theorem, that work done is equal to the change in kinetic energy. Well, we could do the same thing for torque, but the equivalent work kinetic energy theorem is that the torque times the angular displacement, not linear displacement, angular displacement, is equal to the work done, which is the change in rotational kinetic energy. So the work by the torque is delta W is equal to tau delta theta, and that's equal to the change in kinetic energy. So if we release okay, let's do this more carefully. Okay, so let's imagine a compass needle held perpendicular to B. And so we'll draw a picture of this. So here's our B, and I'm going to take my compass needle, something like this. This is the north side. It's going to rotate about this axis. Here's the south side, and theta is going to be here, and our compass needle will tend to rotate into this new position where theta has decreased. All right. So if the needle is released, released, theta decreases, delta theta is less than 0, and the kinetic energy increases. We started from rest, and then as it moves towards that new orientation, it starts going faster and faster and faster. And so our delta K should be positive. Well, if we have a delta theta that's negative, a delta K that's positive, our torque better be negative. And that works because our torque is mu cross B. It's out of the board, but that's in the opposite direction of theta, which we measure in clockwise rotation, but out of the board is associated with counterclockwise rotations by the right-hand rule. So that's all consistent. All right. So therefore, our torque is less than 0. And so our torque is going to be minus mu b sine theta. Okay, and so we already said the magnitude was going to be mu b sine theta. Now we've determined that it's actually a negative torque. And so what we're going to do is put in that minus mu b sine theta for our torque here, and then see if we can work out the energy of our dipole in a magnetic field. All right, so therefore, the change in kinetic energy is torque, which is minus mu b sine theta, times the change in angle delta theta. Now, the electric force and the magnetic force are conservative forces. That means mechanical energy is conserved. If our kinetic energy is increasing, then our potential energy is decreasing by the same amount. So delta K is equal to minus delta U for conservative forces. And that means that delta U is equal to mu b sine theta delta theta. All right, good. So if we imagine our compass needle starts horizontally and then ends vertically, we're going to calculate the change in potential energy. And so we're going to start and we'll say the potential energy at some final angle minus the potential energy at some initial angle is equal to mu b. The integral from theta prime is theta to, theta naught to theta of sine theta prime d theta prime. Okay, good. Now, when we integrate the sine, it becomes minus cos. So we'll pick up a minus mu b cos theta from theta 0 to theta, which is minus mu b. Let's see, cos theta minus cos theta 0. So u of theta minus u of theta 0. All right. So we want to clean this up a little bit. And so we're going to adopt a convention. The convention we're going to adopt is when our compass needle, or equivalently our spin, is perpendicular to the applied field, that's going to be like a theta 0 is 90 degrees. Then we're going to choose that to be 0 for our potential energy. We can choose our 0 potential energy wherever we like. I'm going to choose that perpendicular configuration for 0. That means when I have my moment aligned with the external field, that's going to be a lower potential energy. That's going to be some negative potential energy. If I have them anti-parallel, then that's going to be my maximum of potential energy. And so that's going to be some kind of positive potential energy. So we're going to go from positive to 0 to negative. That's the convention we're going to use. So by convention, we take mu equals 0 when theta naught is equal to pi by 2. Okay. Well, all right. If I put theta naught as pi by 2, I'm going to choose u to be equal to 0. So that means we have 0 here. If I put in pi by 2 for theta naught, I have cos of pi by 2. That's 0. And so that's quite nice. And we just get that the potential energy is minus mu b cos theta, which is equivalent to minus mu dot b. And so that is the energy of our dipole in an external magnetic field. It depends on, of course, the strength of the dipole and the strength of the external field, but also their relative orientations. All right, good. So quantum mechanically the energy associated with a spin in a magnetic field is, let's see, H is minus mu dot B. Okay, so it's the exact same expression. We just replace the energy with our Hamiltonian operator. Now, we've previously said that this magnetic moment is going to be some proportionality constant gamma times the vector spin operator. Okay, and so that gives us H is equal to minus gamma at B dot S. It doesn't matter which order we write our vectors in the dot product. That's quite convenient because we already know all of the matrix representations of all the different spin operators. And so we could immediately, once B is specified, write down the appropriate Hamiltonian. Okay, so the special case that we want to consider is a spin 1/2 particle in a uniform magnetic field, and we might as well align our magnetic field with the z-axis. If I'm going to make a uniform field, I can point it in any direction. It's convenient to say the direction of the field specifies our z-axis. Okay, so if we do that, B dot S is going to be B naught K hat dot S, which is just going to be B naught SZ. And so SZ will be our Z component of the spin angular momentum as an operator. Okay, but we've represented that operator as a matrix already. So we get our B naught. Our matrix had a prefactor of h bar over 2. And for SZ, the matrix was 1, 0, 0, minus 1. Okay, and so then, like I said, we could write down our Hamiltonian more or less immediately. We just take this for our dot product, multiply by minus gamma, and it's done. So our Hamiltonian is minus gamma B naught h bar over 2, 1, 0, 0, minus 1. Okay. I mean, the Hamiltonian is basically SZ times a bunch of constants. But we already know all of the eigenstates for SZ. So that means we know all of the eigenstates for this Hamiltonian, which means we could write down the energy of these states right away. So since H is proportional to SZ, H and SZ have common eigenstates. And they are exactly chi plus, which is 1, 0, and chi minus, which is 0, 1. Okay. So, yeah, all right. So H times chi plus is going to be minus gamma B naught h bar over 2, 1, 0, 0, minus 1, and chi plus is 1, 0. So we have minus gamma B naught h bar over 2. I mean, we better get 1, 0 back. 1 times 1 is 1, and then 0 times 0 is 0. So we get 1, and then 0, 0. Okay, so that works. 1, 0. And so the energy of the chi plus state is minus gamma b naught h bar over 2. So the other one is very similar. The Hamiltonian, of course, is exactly the same. All that changes is our eigenstate. Okay, let's see. 1 times 0, 0 times 1. So we get a 0. And then we get, let's see, 0 times 0, 1 times minus 1. And so we get a minus 1. Something. Oh, no, that's right. Okay, good, good. That makes sense. So I'm going to bring out the minus sign. And so we get a gamma b naught h bar over 2, 0, 1. And so the energy of the chi minus state is plus gamma b naught h bar over 2. Okay. So a couple of things that we should really focus on here. First of all, if there was no external magnetic field, if we turn the field off, so B0 is 0, then the energy of the chi plus state would be 0, and the energy of the chi minus state would be 0. I don't really care that they're both 0. What I care about is that they're exactly the same. So with no external fields, the spin up and the spin down states have the exact same energy, and that's called degenerate. So those two states are degenerate in energy. So when the external field is off, or 0, let's say, so B0 equals 0, the spin up and spin down states have the same energy. And they're said to be degenerate. When we turn the field on, they split, the two states split, and the splitting is proportional to B naught. In fact, the difference in energy between these two states is gamma B naught H bar. And so I can make B naught whatever I want, and I can make the splitting whatever I want. So the magnetic field is tuning how far separated the two states are. So when B naught is not equal to 0, the degeneracy is lifted, and the states split in energy by an amount. Delta is equal to gamma B naught H bar, or it's proportional to B naught. All right. So it turns out that for electrons, gamma is negative. And so this plus gamma B naught H bar is actually a lower energy state than the minus gamma B naught H bar over 2. So for electrons, gamma is negative. So I think gamma is equal to minus 2 times the electron charge divided by the mass. I should say it's approximately, it's very close to that value. There's little corrections that we won't worry about. But because it's negative, this is the lower energy state. The spin down state is the low energy state. So this is the low energy state. And the spin up state is the high energy state. Okay, good. All right. So we have a Hamiltonian, and so we should be able to write down the time-dependent Schrodinger equation. All right, so the time-dependent Schrodinger equation is, okay, it was IH bar d by dt acting on the wave function is equal to the Hamiltonian times the wave function. And I'm going to use chi for the wave function because we're talking about just our spins right now. All right. But if we go look at our Hamiltonian, where is it? There it is. There's nothing that involves time in here. Gamma is a constant, H bar is a constant, B naught is some static field. There's nothing that depends on time. So we can work with this time-dependent Schrodinger equation. Since H is independent of time, we already know what's going to happen. The evolution of the eigenstates are going to be e to the minus I times the energy times t divided by h bar. But let's just prove it again. It'll be a little mini review. Okay, so we could write this as d chi divided by chi. And then it's h minus I over h bar dt. Just rearranging terms. Now, if I integrate, I'm going to get the ln is equal to this stuff times t. And then I take the exponential. I'm going to get chi is some constant times e to the minus I h t over h bar. Okay, and so we end up getting chi of t is equal to chi of 0 e to the minus I ht over h bar. So I e t over h bar. I guess, well, okay. Maybe I should have. All right. What I should do is say h acting on chi gives us the eigenvalue times chi, and then I'll put an e here. That's better. All right, good. So if chi 0 was equal to a chi plus b chi minus, which is AB because this is 1, 0 and this is 0, 1, then at some later time, chi of t is equal to, well, it's the same thing, a chi plus, but then we introduce this little complex phase factor. So it's e to the minus I e plus t over h bar plus b chi minus e to the minus I e minus t over h bar, where we should write that where are our eigenstates. And so this is going to be the E plus energy, and this one is going to be the E minus energy. It's a little confusing because the E minus has the positive energy and the E plus has the negative. But this minus and this plus corresponds, what it's really telling us is it spin up or spin down. So the spin up has the negative energy, which happens to be the high energy for a negative gamma. Okay. All right. Good. So that's A chi plus E. So this one has the negative sign, so it's going to kill that minus. So we'll get an E to the I. And what was it? Gamma B0 T divided by 2 plus B chi minus E. This minus sign stays because the E minus was the positive one. And so we get a minus, sorry, E to the minus I gamma B naught T over 2. And so what you can see, and it's worth noticing right now, is that these evolve with the same sort of time dependence, but one of them's negative and the other one's positive. So if they start at some particular phase and we let time evolve, they evolve in the opposite direction. So that's just worth keeping in the back of our mind. All right. But this is 1, 0, and then this is 0, 1. And so we could write our state as a nice, clean matrix equation. And so let's do that. So chi of t is equal to a column matrix that's A, E to the I gamma B naught T over 2. And then we have B, E to the minus I gamma B naught T over 2. Okay. This gamma B naught, let's see, what kind of units does it, sorry, I forgot, I'm missing something. What am I missing here? I see, okay, sorry, I'm not missing anything. Our energies had H bars in them, but then we divided by H bar, so that's correct. Okay, so that's okay. So what I did want to say then is the exponential has to be unitless. So we have a t in there. So t, let's say, has units of seconds. So this gamma b naught must be inverse seconds. And so it's very common to express, let's write gamma b naught equal to omega naught with the units of omega naught is 1 over seconds. Okay, so then chi of t is equal to A e to the I omega naught t over 2 B e to the minus I omega naught t over 2. And then if we wanted to, we could factor out the exponential from the A. And then B. If I factor it out from the A, I have to factor it out from the E as well. But if I take out plus I omega naught t over 2, I'm going to end up with minus I omega naught t not divided by 2. Okay, so this is going to be e to the I omega naught t with a minus sign, and there it is. So that is the time evolution of our general spin state when we're in a magnetic field. So this is the time evolution of a general spin state in an external magnetic field. All right. What we'll do next time is we will try to calculate some expectation values for the spin, and we'll see what we get. What this is all going to lead to is precession of the spin in a magnetic field. And the precession will occur at a frequency omega naught. And it's the precession of the spins of a large collection of spins that leads to the actual signals that are detected in an MRI measurement to try to image sort of the internal structure of the body. Okay, but we've got a little more work to do to get there, but it's actually not too much. We're almost there. So we'll finish this off next time on Wednesday, and then I'll probably work through a couple of additional example problems, and that's how we'll wrap up. All right, that's it for today. Thanks very much, everyone, and we'll see you next time.